So I think when we stopped, we said that this equation, which was the average signal power, which is IRMS, we have this like VRMS and IRMS and cosine of phi. Right? So we sort of understand that by looking at phi, we are able to say something about how much signal power is there or how much signal power is not there. Right? So because we want to sort of, use this for certain instances, we call this cosine of phi something called the power factor. Right? That's the name that they give this power factor. And then if you go and ask anybody in the industry, they have a little thingy, right? They have this unit which is called the power factor correction unit. Right? I guess last year I had this with me. I had a little one with me. This year I couldn't locate it. I must have dropped it somewhere. There's a little grid that you can buy from the store. All industries, they bring this and they fix this on the wall and they connect it across their system. I'll tell you what exactly it will do for the system. So, of course, they are not interested in any of these things when it comes to home environments, because inside home environments, you of course have inductive loads like I said, there's the blender and washing machine, but those will not create a significant change in your, the angles. It doesn't incorporate significant amount of inductance into your system. So you don't need any power factor correction stuff when you use your home system. But here I will show you. Let's say, for example, you have so here this is like Lakshapana, right? Lakshapana will generate some electromotive force, EMF, so comes to your house. Then, it's not coming to your house, it's coming to your industry, like a little motor kind of thing. So you have your industry. So I have to draw an equivalent circuit for your industry. And then the industry people, because they don't want to pay a lot of money, because they charge you for reactive and active power. I'll tell you a little while what is reactive and what is active kind of power. I will tell it to you like now. No, I'll tell you later. Right? Then on top of that, base industries come and hook up something called the capacitor bank. Right? Capacitor bank. Now we will try to analyze what happens with this. So if I look at industry with a lot of motors and stuff like that, if I draw an equivalent circuit, it is going to be a resistor and an inductor. R and L. It's going to be a resistor and some inductor. Then they have this unit that I can buy from the store, which is a capacitor bank. Right? So essentially, if I drop all of the boxes, all of these boxes, your equivalent circuit of some industry where you get some electricity from your source is something like this. Right? This is R, this is L, this is C. Now we know that if you want to create some sort of if you want to create an AC circuit out of this, we have to place these things with their AC equivalent. So how would I do it? I will replace this with R, replace this with JL omega, and I replace this with 1 over JC omega. Right? That's what I'm going to do. Now, I think this is also your lab. This is your lab, right? I think second lab maybe. I guess lab number 3 was something like this. Okay, so you are going to do this. Of course, you are not talking about machines and stuff like that, but this is what you are going to do. So now, let's say, for example, this loop has a current flow of capital I, you will realize that if you apply the, Ohm's law, that's going to be capital I times R plus JL omega plus 1 over JC omega. Right? So if I E equals IR or V equals IR, this is what you get. So at the end of the day, you will have E is equal to capital I of R. Now here I can put this down as plus J, this L omega, that's minus 1 over C omega. So now this is a complex number. You can see it is a complex number. Now basically using that particular complex number, I can find the voltage drop which is across the resistor. You realize the voltage drop across the resistor is going to be capital I times R. Right? So this is going to be equal to E, right, times R over R plus J times L omega 1 over minus C omega. Now this is a complex number, right? Please keep in mind that this is a complex number. Then you can find the inductive, basically the voltage drop across the inductor, as what? As I times JL omega. Right? I times JL omega. So that will give you JL omega times E over R plus J times L omega minus 1 over C omega. In the same form, I can also say that VC is equal to I times 1 over JC omega, and then I can write down the equations for that. Now you realize these three, right? These three, VR, VL and VC will change with the change of this frequency. Right? Because if you change this whole thing is going to change. If I take this as a complex number, the R theta, the angles and the magnitudes are going to change. Right? They are going to change. So you realize, you take a frequency, these things are always changing. If I change the frequency, something is going to change. But we have to figure out how this is going to change. So let's take a look at this. And just look through this system, and let's try to find an equivalent impedance that when we look into the system, how it's going to react. So if I find R of TH, that is nothing other than J of capital L omega 1 over C omega. So if I find this magnitude of R of TH, I will get R squared plus I got L omega C omega squared of root. Now I just want you to go home and choose an R, L and C value, some R, L and C value for different values of the frequency. Omega. Just choose some sets of values of frequency. Draw the graph of R of TH. Draw the graph of frequency versus R of TH. You realize this is going to change. You are going to realize that this impedance is going to have a low value at some frequency. Rest of it, this is going to be higher. And I will also show you, I'm sure you are going to do this in your lab, so I'm not going to do that part of it. You are going to realize this minimum of this value of omega is going to come when you have L omega being equal to 1 over C omega. When that part is equal to 0. Because why? This is a square element. If it's a square element, whatever you have here, it is going to be greater than 0. right? It will become equal to 0 when this equals that. And that will give you this value of the omega star at 1 over root of LC. This is what is called the resonant frequency. In fact, that is the idea that they use for your radio. Do you realize that? That is the idea they started using for your radio. Radio, you turn this button thingy, right? They find different frequency values for which your system will begin to resonate. Then you hear that particular radio channel, right? This we will do that later, not today, right? So you realize this is the frequency at which it becomes lowest, right? And then you also realize something. At that point, when omega is equal to omega star, this becomes what? Completely resistive. The circuit at that point will become completely resistive. When it becomes completely resistive, tell me the angle difference between the V and the I. If my circuit is a complete resistor, if I send in V through it, what is the angle that this is going to change from I? 0. There's no angle difference because if it is completely resistive, we have already shown resistor, you have I and V, no angle difference between them as it passes through. Which means what? Which means basically the power factor at that point is what? Power factor is 1. Because why? The angle phi is 0. If it's 0, what do you have? Cosine of 0 is 1. What does it mean? That is the ideal case. Ideal case. That's when the maximum signal power is actually dissipated. Right? Now, I want to take you back to this diagram, to this particular diagram, and try to draw the phasor diagram. Now, you can please remember all this time you were drawing the phasor diagram for an individual element, resistor, capacitor, and inductor. What happens if I put all three together? What happens if I have all three together? Now, if I have all three of them together, the only way you can draw the phasor diagram is to find out the common, right? First thing you need to do is to find the common element that will go across all these three. You realize that is I. See, this goes through that, and that. Then what happens is in your phasor diagram, your capital of I would be the reference. If your circuit was completely parallel, then the voltage is the one that is used as the reference, right? Because that's the one that is equal to all three. Here you realize this is the one that is going through all three of the elements. Now let's see how we can draw the phasor diagram. Now let's say, for example, here the voltage drop was VR. Here the voltage drop was like VL. Here the voltage drop is VC. Right? Now you know that this VR and I can't have a phase difference. Why? Because you already know that. So your VR should be in phase with I. We have drawn this several times. No phase difference. If you look at the inductor, where would it be? Yes, where would it be? Now you understand. I have already told you CIVIL. If it is inductor, V should lead this I by how much? By 90 degrees. So this is I, that is V. right? That is VL. So now into the phasor diagram we have put two things. And the third thing we are going to put is this voltage, which means I has to lead V by 90. That can only happen if I put VC here. See, VC, this is leading that by 90 degrees. Now, forget about the fact that this is a phasor diagram. Forget this is a phasor diagram. You have done in your advanced level complex numbers, and something called parallelogram law. Yes, V square plus R square plus 2V cosine something. Yeah, I don't know. Something like that. Right? So if you completely forget this particular phasor diagram, completely forget the phasor diagram. If you had like a vector here A, vector here B, vector here C, this is equivalent to you having a vector here B minus C and a vector here A. Then you use your law to find the resultant using a graphical method. Magnitude of this square plus magnitude of that square plus whatever the angle. That's what you do. I can do the same thing here. Right? I can do the same thing here. If I do the same thing here, right? If I do the same thing here, I would get what? This is VR. You realize this is VLN, that is VC. I can rewrite this like that. VL minus VC. Then you have VR here. Right? If I put them together, I would have a resultant going that way, and this is I, and that angle is what we call that angle will take the cosine of that is what is called of the power factor. Now keep this in your head. Take a look at this. Basically what I am saying is that if this part is equal to 0, I am essentially saying that JL omega in terms of its magnitude is equal to, in terms of its magnitude, 1 over JC omega. Yeah, see, this is what I am saying. If this is equal to that, what happens? These two are equal. Which means what? If I go back to this diagram, I am saying that this is equal to 0. Right? I mean, say that this is equal to 0 because this is equal to that. If that is equal to this, what would my phasor diagram be? VR and I. That's why it is completely resistive. Right? That's why it's completely resistive. But if it is not resistive, that is going to get offset by some value. Right? In fact, what all these industries are trying to do is this. This is what the industries are trying to do. You know, basically what they have is you have VR and I, and you have VL here. Right? This is what the industries have. Because why? They have an inductive load. All these machines. So you have a resultant force going like that with an angle phi. Right? Essentially what they are trying to do is to bring themselves a capacitor band, fix it onto the thing, so that you are going to add a capacitive reactance to that side, so that when you take this becomes lower. That's what they are trying to do. Then they put an automated capacitor bank so that they can make this almost equal to a resistor. Because why? If they don't, they get charged for reactive signal power. So they put a capacitor bank in front so that this one which is vertical is negated by the other one which is going at minus 90, so that the entire thing becomes resistive. Right? This is one of the most fundamental on getting this little unit which automatically finds out the inductive load and adjusts the capacitance to actually take out that effect, so that they make it completely resistive. And when it becomes completely resistive, it's like a home unit. You are getting charged for simply I squared R. Right? That's what you're trying to do. And this I squared R is what is called the active signal power. Because that's the one that you can see. Right? I squared R. You read something and touch it, boom, I squared R. You can see active power. And the other part you can't see. That's basically reactive power. Sometime back, they were telling we are generating power, people are using the signal power, but payment is very small. Because why? They can only charge for this, they can't. The portion that goes to vertical axis, they can't even see. What they can see is the portion that goes on to the horizontal axis. And then you know from your advanced level, I guess, knowledge, right? You probably know from your advanced level knowledge, if I have something like this, the only path that goes here is like what? If this is if this is the P, the only path that goes here is P cosine phi, right? And how much is the P? That's the VI, VRMS, IRMS. Cosine phi. See, there you are. That's why they made sure that you had a capacitor bank to make sure they see all the power and they only charge for the power that you use. Because basically, if you go to deficit mode, they charge you a tremendous amount for reactive power. They charge you 5 to 6 times more if the reactive vehicle is there. Right? So nobody wants to pay for reactive power. Right? So they will, and also what happens is you have a lot of reactive power in this. Basically, you have a lot of inductors. That is going to really influence you also. Right? Because your lights are going to be dimmer. Because now it's coming at an angle. So what you are seeing is actually V. It is not really V that you are seeing. V of cosine of phi that you are going to see. So all the lights are dim. So nobody wants that happen. So they have to encourage the people to use that technique to make sure that the basic inductive power is taken out. And how do they do it? By charging them 10 times as much for that versus the regular reactive power. Okay, so now I have given you a little bit of an idea of how to draw the basically the phasor diagram and all that. So here, so now I want to come and tell you a statement. Here's what I'm saying. Basically, if it is R, if it is anything to do with the resistance, this is going to generate what is called the active power. Right? Active power. And active power in your advanced level, you have known with the units watt. Right? Watt. Then, if it was anything to do with reactive, which is imaginary part, right? Which means anything to do with a Z. I guess either it is JL omega or it is like 1 over JC omega or any sort of mixture of this, where there is a J component, you will be dissipating. You can't even call it actually. You can't call it dissipating. I will also explain that to you. You will be putting out some amount of power which is called the reactive power. Right? Reactive power. And because people wanted that particular power to be sort of recognized in a separate manner, they call it voltage. Right? Voltage ampere reactive. They call it VAR. Right? VAR. VAR. Then, if I put these two together, so basically this is going to be the reactive, this is going to be the active active power. What is going up here is going to be the reactive power. If I put both of these things together to find a resultant sort of power, that is called, of course, this is like, I guess, known as P. It is active power. If it's here, capital Q, because they want to show it is like a reactive power, and this is called apparent power, which is basically addition or simply the resultant of those two other powers, and this is known as VA, right? Volt amperes, and that is known as S. In fact, if you take a look at the book, you will see something called something like a triangle, something like this, where this is P, that is Q, and S. This is called the power triangle. I think that is in your advanced level, right? Because I saw an examination paper where they asked you something about the power triangle, right? The power triangle. So, and then also we can figure out that this particular power factor, cosine phi, is called the power factor, right? Is that okay? Right? Now, within a very short period of time, I gave you a lot of information, right? Tremendous amount of information. It is not yet over. I'm going to put some icing on top of that also. Please go home and work on these problems. As I told you, I will not be asking any of these questions except for about 2 little questions, because I want to find out who understood this the first time. Right? Who understood the first time. But everybody else.
The reactive power is invisible. How do they measure?
Huh?
The reactive power is invisible. I mean, the sense that how do they measure?
Oh, they have some ways of doing it, because you know what you are really finding out the angle, right? Though when we draw it, we say it is imaginary.
So can we sense the angle?
Yeah, that's good. You can find the basis. Base sections you can find. So it has a little equipment in there that actually finds the base and then figures out how much reactive power is. Right? I didn't want to go to that level. Because it is vector. Now, I want to extend this. When you say extend, you go, right? And I actually want to show this to you. What is this reactive power? What is this active power? Right? I just want to show this to you. You're thinking, no, please don't show it to us. We have enough things on our mind already. Here. So if I take a resistor, right? Here's what I'm going to do. This is voltage. That is if I draw it in blue, that is like voltage. If I draw it in if I draw it in red, it is going to be the current, and then the P, which is equal to like VI, is drawn in green, right? Okay. So let's start from here. If I have a resistor, right? If I have a resistor, I realize voltage waveform is like this, right? You have the current waveform. I don't know. It can go over or under. I don't care. Current waveform like this. If I draw the P, which is VI, you already did. It's going to be what? Something like this. Everything is plus and plus. This is why we can like measure it. It's plus. Now, we will draw the same thing. So this is fine. This is what you did earlier. We will draw the same thing for an inductor. Right? So if you have an inductor, if I have I, inductor is L of di, right? L di by dt. So I have red, this is I, right? And that is V. Right? It is like 90 degrees out of phase. This is V, that is I, and now if I just multiply, what would I get? So you realize this multiplication will go where? This goes up, this goes down, and over here this is equal to 0. See, this is 0. So it will go like this. Right? If I do it here, this side is greater than 0, this side is less than 0. So, and you realize this is equal to 0. So, if I do the multiplication, that's what I get. How about this one? This is minus and like minus, though it's plus, but here it is 0. So, I get this. And this is, so, that's how it goes. Right? Now what has happened? Here, this side is plus, this side is minus, this side is plus, this side is minus. So across an inductor, you have what? You have this power being dissipated, power absorbed. Power dissipated, power absorbed. See? If I take overall, no average value. Which means what? No active power. No active power. Because why? If I take the average of all of these things, this is like a sinusoidal signal. This is plus. See? This is plus, minus. Plus, minus. If you add up, it will just be 0. So, this is not like a resistor. Resistor is what? Resistor is always giving out a maximum power, giving out basically 0 power. It's not absorbing any power. It's always dissipating. So this is the particular reason why if you have an inductor, nobody says there are power dissipations. So then you can't say. You don't know once it is going to dissipate, others it is going to absorb. It's the same as it goes through the cycle. So this one will dissipate, right? You realize over here it is going to dissipate, here it is going to absorb. So signal power is absorbed and dissipate, absorb, dissipate, absorb, dissipate. Same thing is going to happen if you are going to draw it for a capacitor. In a capacitor, you have, this is V, right? This is V, and this is I. It is 90 degrees out of phase. Again, you would see what? This is plus, at this point it is 0. There you are. See? Plus, minus, absorb and dissipate. Right? So I just wanted you to see this so that you look at it and go, oh, yeah, it is dissipating, yes. Yeah, very nice. Now, let's do a problem which brings all of these things together. Have I put everything together? Oh, I think okay, let me give you some sort of like definitions before I go. Okay, quiet. right? Let's write this as notes on power. This is the most important part, right? We will say V is equal to Vrms with an angle of, let's say, theta V, right? That is the, I guess, right, voltage waveform. If I is Irms with an angle of like minus theta of I, right? Minus theta of I. Then you can say the power factor is what? Cosine of the angle difference. Actually, no, this is plus. Theta V minus theta I. Now, if I ask you to draw the phasor diagram, this is your what? Reference. Yeah, reference. This is what? Vrms with an angle of theta V. So there you are. V with an angle of theta V. Then I is Irms with an angle of theta I. So let's say that's where you had I. That is your theta I. So we will take your theta I to be smaller than theta V. Now, immediately from this equation you see what? The power factor is the cosine of the angle difference between V and I. See? Angle difference. So this is the most important part that you need to figure out. So the angle that you have here, which is the difference between V and I, is theta V minus of theta I. And the cosine of that is what is called the power factor. Right? So, you have ideal situation, you want it to be what? Theta V should be equal to theta I. That's the ideal situation. Then what about V and I are on the same line? Which means what? Your circuit is sort of resistive. Right? That's what you want. Ideally, that's what you want. Then, you have what is known as active power, right? Which is also called real power, which is what you can see, is also known as P is equal to Vrms and Irms of cosine of this angle. And that is denoted by what? So, the active power is the cosine of that. So, which means how much of V is on top of I. See? In the same way, you have what is known as reactive power, which is called by imaginary power. It's also known as capital Q, which is Vrms into capital Irms. Rather than cosine, we look at how much of it is at 90 degrees. It is going to be sine of theta V minus theta I, and this is known as volt ampere reactive. So essentially, you are finding some part that goes through this and another part that goes in like right angles to that, right? Because you realize this is going to be V of Rms sine of theta V minus theta I, and basically this part is Vrms cosine of theta V. So basically you take the You take the you simply take the cosine part and just multiply it with I. You get this one. You take the one that imaginary and then multiply it with I. You get something called the reactive power. Right? And then you have apparent. Apparent power, which is also like known as S, which is P plus J times Q. Because why? This is the part that is imaginary, 90 degree part, right? And this is denoted by volt amperes, and this is also equal to Vrms into capital IRMS. It doesn't have an angle, and that is in volt amperes, right? Volt amperes. Right? And then if you can simply add everything together, this angle is phi, this is S, that is Q, this is P, and we know that is called the power crank. Right? Is that okay? Now I also can do another problem here, right? I will do a problem which uses all these equations from top to bottom, right? If you can understand that problem, more than 50% of what I just taught is in your head, right? The rest of it you have to learn very hard, right? Usually during this, after this particular session is over, people start drinking water and then ask what is happening to the air conditioner, why is it not cold enough? Yeah, this is a difficult part to understand. But I think some parts of this is already handled in the advanced level, if I'm not mistaken. Right? But don't worry about it. I went through everything that you need to know here to actually do this particular set of problems. Now, because anybody can actually, this part is actually useful, because now you can go home and find how much electricity is used in your house using this equation. Right? The V and I, you can measure. Probably not, because I want my class to put it. I don't want anybody to get that. Right? Poke your finger, say something, and then. So let me give you a very simple question which uses everything. And also, folks, I am going to have this I think I have division class for you on I think Thursday, right? During the mechanics lecture, I am taking the mechanics lectures. If you have any problem that you want me to do in the class, please you have to send it to me, right? But don't send me problems that are not worked out. Now, I have a ton of problems that I want to work out in my phone. All of them have been worked out. Right? I will not do any problem that you just take a picture and just send it to me. I want to do it at least halfway. Then I here this has been answered. Yeah? Then I do the other part. So all these questions that I got over the net, I'm going to answer when I come back for that class, initial class. There is no shortcut. There is no shortcut into this lecturer systems class. You better figure it out quick, because two groups thought that there was a shortcut to this. There is no shortcut. Long, tedious, do the questions, understand kind of situation is necessary to pass this class. And do not look at the sample examination papers that have given in the previous years, because like that the format changes, right? I can give anything, but I will tell you what I am going to give. So I will say First question is about mesh analysis. You have two loops. You are supposed to do it using this mesh analysis. So source transformation is done in the first part. Second part, I guess only thing you wouldn't know is what are the R values and the J values that are going to give. So the question itself is already known. So I mean, I guess there are some people who in their A4 science paper they just like wrote down some of the questions that I did, hoping that the question might look something like that, right? Highly unlikely, but you can. I didn't say what you can put and what you can't put in that question, right? You can put anything you want. Some people are reading tiny lettering, the entire 6 weeks of notes was on 2 A4 paper, 1 A4 paper. That's fine, right? I think ask me not. Right? Only thing what I want to know is, do you know how to solve that problem? Right? If you know how to solve that problem, I'll give you the marks. Because I think you can get marks from the midterm. Don't wait until the final to get marks. Right? It's not going to happen. Midterm thing. Right? And then also, as I told you before, your second chance is not going to come at the end of the year. What I did for the earlier batch, we are not going to do it again because it's a clear aim to do this. Because the students, when you try to have figured out that the state students are not mature enough to get help. So when I try to help them, they try to twist my arm, which is not very good. Right? Made me a very angry man. I said, this time I'm not going to, because I give them a repeat paper to do, and these guys come and tell, oh, I didn't see the thing, I didn't come for the paper because I was not notified in time. That kind of bullshit doesn't fly with you, right? So I gave one, and some people failed, and some people were told them. I was not informed. How is it? This is fine, right? So you have no choice but to pass this time, but you can move forward. Right? When we have 5 courses that you are going to fail, you can move to the next year. I guess you know that. Right? Which is very bad for you. Because I'll tell you why. If you move forward with more than 3 courses that are failed, we as an institute are going to make a lot of money out of it. Don't give the institute that chance. Right? Because we have found out that people who fail large numbers will accumulate their failures. And at some point in time, you get stuck for 1 whole year. And that famous is very difficult. Right? It's better for you to stay back for 1 semester, finish it, and go to the next semester. It is very cheap for you. Right? But some people want to go, drag their luggage and go to second year, another 2 subjects get added, so 4 plus another 2 is 6. Next year, 4 plus 2 plus another 3. So at the end, they got all 20 courses that are going to be pending. When we were doing undergraduate studies, when we did it for the year 1, first year, was a rude shock for us. Because we are used to advanced level. We also went through that. Actually, this was a diagram that was drawn by like one of my students, right? Here is the stuff that you need to know in the course, right? Here is the stuff that you need to know. And then here is the stuff that you understood. Right? Here is the stuff that you understood. And this was what the exam paper was. Right? This was a real picture that was drawn by a student and sent to me. So that was your class. I said, no. What I did was, I said, this was the exam paper. Right? So it's okay. This is not something that is only felt by you, because I know when I saw the thing on the Facebook, I realized nobody told you this, because they were saying all of the I guess lecturers who have come here are from the state universities, right? They will not teach you. They will say, oh, okay, it's there, I'll be there, and then They expect you to learn. We do it. We can do courses, we can do extra classes and teach you everything, but we don't, because that's not what is necessary for you. You have to be independent. You have to learn. You have to do the problems. You have to do it by yourself, because this is the only chance for us to teach you to be yourself, like an independent person. A-levels did not allow you to be independent. Did they allow you to be independent? I heard a sad story. I heard from one person that their kid went for 26 classes. How many subjects are there? About 3 or 4, right? No, don't laugh. You have done it too. You go for physics. You go to Mr. A. You go to the Mrs. X, right? Just to be safe side, you go to Mr. B also to see what he is saying. Don't tell me you didn't do that, because that's Yeah, that's what kids do these days. They go from one, so they need a secretary to organize their day. One class cancelled, they go all crazy. Yeah? Don't worry about it. One of your other persons in the batch, that was the previous batch, got so worked up. I see her at 6:30 in the evening, seated near the parking lot, on the other side, seated on a bench studying. She was going like this. I was thinking to myself, hey, you don't have to understand everything. You probably will not understand everything at the end of the day. But you have to learn the tools. See, when I teach you the problem, what do I do? Do I talk about the problem? No, I say, this is the rule. Rule is what is important. Then anything you can apply to and then get the answers. Right? So we are very sad that you feel like that, but nothing is going to change. We will not spoon feed you. Right? In fact, we will not even use the spoon to feed you. Right? But you will make it at the end of the day. Believe me, you will make it at the end of the day. Here is the question. We got 15 minutes. I will show you how this question can be done. Now listen very carefully to this, because this is very essential for you. Here, this is a very simple circuit, which is an RLC circuit. This is E, that is going to be 10 with an angle of 0. This is R, which is going to be 25 ohms. This is L, which is going to be 0.636. Now here they give you the inductance, right? Then you have C, which is equal to 14.14 farad. 14.14 farad. And they give you the frequency as 60 hertz. Right? Which means what? Frequency 60 hertz means omega is what? 2 times pi times f. That turns out to be 377 radians per second. Now we have to transform this into an AC circuit. So to do that, if I want to transform this to AC circuit, this becomes 25, right? You realize this becomes J times L, which is 0.6365 into the frequency omega 377, which works out to be J200, right? J200. And this one, if I want to transform this into an AC circuit, that will be 1 over JC omega, which will be like minus J over C, which is 14.14 times 377, the frequency, which works out to be there is something wrong with that. I think this is microfarads, right? So there is into 10 to the negative 6 into 377, and that turns out to be negative J 225 ohms, right? So now we have converted this into an AC circuit. So if I use this particular current to be capital I can immediately apply the basically the Kirchhoff law to say that this is equal to 10 to the 0 E over all these R, which is equal to 25 plus J 200 minus J 220 25, and that will be equal to 10 with an angle of 0 over 25 minus J of 25, and 25 minus J of 25 I have basically worked it out to be 35.4 with an angle of minus 45. All these things you can go home and check, right? And that turns out to be 10 with an angle of 0 over 35.4 with an angle of minus 45, and that is equal to 0.28 with an angle 0.28A with an angle of 45. Right? Now that is a straightforward calculation. So you have E to be equal to 10 with an angle of 0, and I is equal to 0.28A. This is volt with an angle of 0, 45 degrees. Now tell me, what is the power factor? What is the power factor of this circuit? Now remember the rule is what? The rule is very simple. Rule means you have to find the cosine of the angle between the B and the I. Now tell me, what is the angle between the B and the I? 45. So your power factor is cosine of 45, which is how much? 0.747. Right? Now tell me, right, whether this circuit is in fact leading or is it lagging? Now you ask the question, do you know how to answer that question? If somebody asks you whether this system is leading or whether this system is lagging, what is your answer going to be? You tell me, out of these two circuits, you realize if I look at an inductor, you have what? V, which is leading I, right? If I look at a capacitor, you have I leading V, right? As a general standard, when somebody asks you which one is leading, you always look at I, right? You always look at I. So if I have it like this is V, that is I, you call that a leading circuit, right? Which means what? Generally, any capacitive circuit is called a leading circuit, right? That's the rule. Now, okay. So usually, if I simply have it like this, I would say cosine phi, right? And I would say leading power factor. These are the sorts of circuits which are called leading power factor circuits, right? So which means the circuit looks more like a capacitor than an inductor. That's what it means, right? The circuit looks more like a capacitive circuit than an inductive circuit. So immediately you will say cosine 45, which is equal to 0.707, and you say leading power factor circuit, because why? This is leading that. And then if I ask you to draw the phasor diagram for the circuit, you realize that is E. There is no angle. Here you would draw capital I with an angle of 45. That is the phasor diagram, right? Just draw the I and the V. Now here, so basic in this circuit, if I look through this to find equivalent, rather than saying equivalent resistance, because there is going to be some sort of reactive part, I call it equivalent impedance. So if I want to find the equivalent impedance, it will be R plus this, right? So I would have ZTH to be equal to base R, which is 25, plus J200 minus J225, which is equal to 25 minus J25 ohms, right? Okay. Now let me ask you, right, what is P? Yes, what is P? Now I already gave you an equation. It says P is equal to Vrms and into capital IRMS cosine of the angle between the I and the V, right? So it is going to be Vrms and capital Vrms, capital IRMS, and cosine of the angle between these two, right? Remember, that's the equation. Now the question is, right, what is Vrms? I told you, if somebody states your equation like this, that is the RMS value, right? Then I, we have realized, which means that is the RMS value, right? So you would basically have here, this is equal to 10 times 0.28 cosine of the angle between those two are going to be 45. So how much is this? It is 1.98 watts, right? 1.98 watts VI and cosine. Now I also told you that this is called the active power, right? Active power. Now active signal power is only going to be dissipated across a what? Resistor, right? Yes, active power is only going to be dissipated across a what? Resistor. Now tell me what is the equivalent resistance of this whole thing? What is the equivalent resistance of this entire circuit? Yes? Yeah, how much? Yes, what is the equivalent resistance? Because you realize this whole network will have a part which is actually resistive and a part which is reactive, right? It will be an addition of those two. So out of that, what is the part that is actually resistive? No? 25. See? This is the part that is resistive. Here, this is the equivalent resistance, or I said equivalent impedance of the whole circuit, and this actually is going to be a resistive part. This is the equivalent reactive part. This is the resistive part. Now, if it is a resistive part, how much is the power that is going to be dissipated across that resistance. You have an equation for it. Tell me the equation. Yes. I squared R. Or you can have it V squared over R. Now you realize this resistance, that is what you have as I. So if this particular current goes through R, you have a active signal power dissipation of I squared R. So it should be what? P is equal to, you have I squared into R. And then how much is I squared? 0.28, that is the, I guess, magnitude squared into R, which is 25. Right? So how much is I squared R? You will realize when you do this calculation, if somebody can quickly do the calculation, that works out to be 1.98 watts. Right? So that's correct, no? Right? Cosine phi and these are the same thing. This and this is, can somebody check it quickly? Because I could be wrong. 0.28 to the power 2 into 25. How much is that? Yes, is it how much? 1 point? Okay. Little bit error, right? Because of the errors of like putting it to square. It's 1.9. This has to be the same. Now, because I want to show you something in this. Rather than just teaching it to you, I want you to see this. Then I have capital Q, which was equal to VRMS and IRMS times, you have basically sine of the angle between these two. Right? Angle between these two. So how much is that? You have 10 times 0.28. This is like sine 45. That will turn out to be 1.98. Okay, can you actually do this and see? Can you do this and see? So this is actually 2.8 over root 2. Hey, by how much is that? 1.9. Right? So if you take a little bit more terms here, you will get it. So this is vast. Remember, in this question, you have to identify the right unit. Otherwise, it's wrong. Right? Then, here. Just tell me, now this was I squared R. Right? In the same way, if I call this R plus J of X, R plus J of X, where this is actually the resistive part, that is the equivalent reactive part. Something tells you that Q should be equal to I squared of X, because X is like R for the reactance. So how much is this? 0.28 squared into 25, which is the X here, which again is 1.98 watts. Right? So you realize you could have used either equation. But here you have to find the equivalent impedance of the whole thing. Then that will have a resistive part and a reactive part. Then you have S to be equal to P plus J. Right? P plus JQ. You can put P plus JQ, or you can have magnitude of S, which is equal to P squared plus capital Q squared plus root, which is going to be the signal power, which is called apparent signal power. Right? That question has all of the equations that you're going to use in this area. Right? So it's a small question. It has all the equations that you're going to use